Welcome back. Today's topic is a little bit of a fire hose of information, so we should go and get started. We're going to be covering variables and arithmetic, and really starting from a foundation of a high level understanding and view of computer memory and how that relates to C variables and the data types that C natively supports. We'll then be looking at what expressions are needed to assign values to variables and to perform arithmetic on those variables. And then as we transition, we'll be looking at number systems, albeit briefly. Number systems really deserve their own dedicated course, which you will eventually have a chance to take. So, talking about computer memory, when I say memory, I'm really just referring to the place where the program's data, as well as potentially its executable code, is going to be stored. It's definitely a very physical thing from an architectural perspective, from a VLSI, very large scale integration, circuit design perspective, as well as a logical construct from the programmer's perspective. Our programs are going to require data, and that data needs to be stored somewhere, and that memory is where that somewhere is. Programming languages, by design, are there to provide us with a higher level view of the contents of what we have in memory, but ultimately, what we are doing is always accessing these binary values, these ones and these zeros in memory. So we have sort of the VLSI perspective or the semiconductor perspective of what we can have for our ones and zeros. And this is SRAM technology, where our ones and zeros are actually transistors stored in a certain arrangement, and that's how we have our ones and zeros. We have what I refer to as the computer architect's perspective, which is memory is really an address port and a data port, and we provide an address into memory and we get some data back out, or alternately, we provide an address to memory as well as some data we'd like to write, and we update the contents of memory. And then we have the closer to the programmer's perspective, maybe our perspective in this course, in which memory is just a series of address and value pairs, where we have addresses in memory, and at those addresses, we potentially have some content, some values in those locations in memory. And depending on what variables we have and what data types we have associated with those contents in memory, we can represent that data in different ways. Here's two mediocre analogies we can try to use to understand memory a bit better. My first one is the mailbox, and I call this a mediocre analogy because it is. But we could say memory is like a set of mailboxes in which the number on each mailbox corresponds to the address, and the contents of each mailbox then would correspond to the data at that address. Okay, that's analogy one. Analogy two, maybe a very slightly better one, is memory is more like a set of lockers in a locker room, and where there's the name on each locker, and that would correspond to the variable name. And the contents then of each locker would then correspond to the value of that variable. That's a little closer to what we would maybe need as programmers, because while we can sometimes directly access the mailboxes, directly access the addresses of our data, we much more commonly want to use variable names to represent data to access our data that we have in memory. So the big picture is that we have variables, and they really just exist as a way of simplifying our references to data that we have in memory. So on the left up here, we have our kind of address and value and content pairs here, address value pairs. That's one way to access memory by providing the raw addresses here, but much more commonly, we want to instead have some variable name, which ultimately the compiler will then translate into an address for us. But our variable names then corresponding to those same exact contents in memory. Our general program flow is going to be the following. We're going to be loading some value from memory. Our programs are only meaningful if they have some data to work on. So we're going to load some value, some data value from memory. That's step one. Step two is we're going to do some sort of arithmetic or logical computation on that data value. We're going to take the temperature value and apply some mathematical operation on it. And then ultimately, our program should be changing something. We're going to be storing some modified value back into memory. And a very simple C code example in our human analogy equivalent would be we can declare in our program, we've seen this very briefly, three int types. And those would just be the name of three different variables, int b, int c, int j. We can declare them on different lines, or we can use the comma to declare them all in one line of our code. And we would have our actual expression. J would be set to equal to b plus c. Going back to our somewhat mediocre analogy with memory as mailbox or locker, that j equals b plus c is actually going to be four sort of separate operations. Step one, we have to get the value of b. So b We have to determine what address that corresponds to in memory. We would load the value at that location in memory. Step two, we'd have to do the same for C as well. So we're taking the money from Bill's locker. That's step one. Step two, we're taking the money from Chris's locker. There's then the arithmetic operation, in this case, addition, which does exactly what it would sound like. We take the value of B, we add it to the value of C, or if it's money in lockers, we take the money in Bill's locker, we combine it with the money in Chris's locker. And then finally, that equal sign is that storing operation. Uh, we would take the value of B, add it to C, store the result as J in our variable J. That would be equivalent to taking Bill's money, Chris's money, combining them, and of course, storing them in Joe's locker. And so, for that reason, because our variables are just this abstraction or way of simplifying our references to memory, at least in C, it's very critical to understand the different data types and what they would then actually correspond to in terms of our locations in memory. There are several other built in variable types in C, but these are the four you would really want to start understanding to begin with. First is char, or you can call it char, but char for character. That is an 8-bit data type. I think it's sufficient to understand that that's a small amount of data. There's 8 bits, so there's 8 zeros and 1s stored in memory corresponding to every char variable we declare. Then there's the int. We'll be using ints a lot in this class. Int is short for integer, and while we can't say necessarily, it is somewhat dependent on the CPU and the operating system and other support there, but generally you can say an int is going to be 32-bit wide. We then have the float. If we want to actually have decimal values beyond just 0, 1, 2, 3, etc., that's for floating point precision or single precision floating point. That's our float. You can see the range of those values is quite different than for our int types, even though it's only also a 32-bit value. And then we have our double type for double precision floating point type. That's just a larger value or larger range for those int types. And our declaration syntax is what's being shown on the bottom of this slide. We can declare a single integer, int my underscore int, or we can actually declare multiple variables of a certain data type on one line of code. When I showed this range on this slide here, where our car type could have negative 128 as the smallest possible value, our car type as the largest possible value could be stored as 127. Well, first off, this is a direct consequence of how we represent our variables as these ones and zeros in memory. And very briefly, as we talk about data representation and number systems, we'll explain why that's the case. But those are also things you can access in your code. You don't have to memorize those numbers. There's actually built-in macros for you that you can access to get car min and car max and int min and int max. Those are defined already in the language for you to use in your programs. And so one of the PPO2 assignments you'll be working on, it's just really asking you to look up the name of those macros and then to print them out to get some understanding of your system that you're executing code on. We can also specify some additional information for some of the built-in types. So that's more of a qualifier in the name of the type. So we have these int types. You can separately specify, I want a short integer. And in most systems, instead of being 32 bits wide, that would actually only be 16 bits wide. We can also specify a long integer or just a long type. And then there's other variants. There's long integers. It really does depend on the system what those happen to be. But when you specify something as being longer, the implication is you need a little bit more range for that value. And consequently, you're going to use more bits to store that value in memory. And you're going to get a smaller minimum and a larger maximum possible for that. In other cases, you may know that your computation and that your program would never need to have a negative number. And that's what we use that unsigned qualifier for. So if I declare something to be an unsigned int or an unsigned car or unsigned short, as we have examples here, the unsigned int is the same exact size as our int. It's the same number of bits of memory, but we're just saying, well, we know at least for this program or this part of our computation, it's never going to need to be negative. It's always going to be representing a positive or number or zero. And consequently, we can take those same 32 bits and instead of going from that negative 2 million to 2 million value, we can use the same 32 bits and have a range of 0 to roughly 4 million value. There are some other qualifiers as well. We'll see static later on. There's a few other qualifiers that we can disregard. I think a lot of that syntax is a little cumbersome as well, to be frank. So declaring something as an unsigned long, That's a lot of text you have to write just to declare a single variable. For a lot of our programs, we'll just stick with chars, which are pretty important, and our integer types. We'll use some of these qualifier types or some of the other ways to specify our variables only when we really need it. So we'll see that sparingly. You can get pretty far with ints and floats and chars in your program, and I think for several weeks we'll be able to get pretty far with just having those. So here's our syntax for the variable declaration and then for the assignment. There's a few different ways you can set the variable. You can set the variable at initialization time. So if I declare an int and I call that int a1, I can initialize the value of that variable right at that point. So I've declared there's an int, it's called a1, and if I know it's going to be 3 at least to start, I can set it right then and there when I've declared the variable. We can also then, the more common case is we can set the value of the variable a2 in this next example at any other time via some expression. So I have some other variable x, I want to multiply that value of x times 3, and I want to store the result as a2. We can use that type of expression. That's the common case. That's what that equal sign is there for. We also will see various functions that not only do things like print a value, they also return a value from the function itself. We'll use a few of those even early on to generate, for example, random numbers in our code. And so we can take the output of that function and assign a variable to the result of that function's output. And then finally, case 4, which we will use for this specific purpose early on, but really only start to understand later on in the course, is we can have an actual direct address of a function. So we use that ampersand symbol to specify I'm passing the address of this variable, the actual address in memory where that variable is going to be stored, and then this particular function is going to overwrite that location in memory. That's the direct addressing way of updating a value of a variable. You'll see this as an issue as you're writing your early programs. C is pretty particular about variable types and doing these assignments. It's an example of what's referred to as a strongly typed language, meaning that every variable has to be defined with a type. The type that you define it with cannot change for that same variable name, and you have to be very careful when doing any type of conversion between types of variables that are of different types. So I can declare an int and I can declare a float. If I want to do work where I'm using the value of the int and the value of the float, I have to be quite careful. Not all languages require that much care. This example is a little nonsensical, but it's an example of MATLAB, which would allow you to take the value of zebra as a string and multiply it by 17. The result may be nonsensical, but the language syntax allows you to do that. C would not allow you to do that. You would get a syntax error if you tried that in C. I think we're ready really to talk briefly about basic I/O in C. We've already seen a little bit of that with our initial first learning module where we were just printing some text. But a big part of the C standard is the assumption that there's some provided standard library or supporting library. And so that you as the programmer don't have to do everything by scratch or from scratch. Learning this standard C library is sort of equivalent to learning C. The actual syntax of C, there's only a few things you have to learn, but understanding the standard library, what you can do with it, how you interface with it, it goes hand in hand with actually learning C and learning how to program in C. C is pretty low level, as we've seen already, compared to some other programming languages. So the standard library maybe does fewer things than what you can expect in most other languages. But at least for now, it's a good way for us to get started with reading values into our variables and outputting the result of those variables using a couple of the functions that are in our standard IO library. We've seen that pound include standard IO.h in the beginning of our programs, and it'll be in the beginning of essentially all of our programs. And when we include that in the top of our code, we're basically telling the compiler to include the part of the C standard that deals with basic I/O, which includes our print function and, as we'll see, our scan function, scanf functions that we have here. We usually want our application to do more than just printf things and scanf things, but printf is extremely powerful. In fact, it's a very powerful debugging tool. You'll see that this semester. When you're having a problem in your code and you come reach out to me or your classmates for help, it'll be really important to know, okay, something's not working. What is the value of your variables? There's a separate piece of software we can run called the debugger that allows you to inspect the value of those variables, but printf turns out to be pretty good at that as well. We can use printf to print out the value of our variables beyond just what the program specification requires you to do, but as a debugging tool, you can learn a lot about what your program is doing, what's working, what's not working, by just adding extra printfs throughout it. Pretty common debugging strategy. It's actually quite powerful. And syntactically, that's what this looks like here. Our basic IO in C, where we're printing out the values of our variables. Um, Using these IO functions, we can actually print any variable of a basic type using a so-called conversion specifier in our syntax. That's a funny word for this percent sign and then a character following it or number of characters following it, where we are saying that I'm going to be printing out this string, and as part of that string, I want to insert the value of a particular variable uh, in lieu of just the actual symbol for percent %d here. So this example we're printing out, I have percent %d dogs and percent %d cats. And each of these are those conversion or format specifiers that are saying, after I've finished up what this string is going to be for printing, I need to then provide the value of, in this case, an integer for our percent %d, and then a second integer for that percent %d for the number of dogs potentially and the number of cats. The order matters, so that's a little bit tricky here. Um, and actually having the right number of those variables corresponding to number of conversion specifiers is also something that you have to be very careful with. It will not always be a syntax error when you do this part wrong. You'll just get some nonsense output that can be a little difficult to track down. There's a lot of variety for what we can provide for those. I don't want us to overthink it. So here's we have our um, example of our basic IO where we're using percent %d and again percent %d for the number of dogs and for the number of cats. We have all the documentation for this and it's linked for every assignment that really requires it. There's a pretty big complicated table that you can really, if you wanted to take the time, stare at, understand all the different conversion specifiers, all the different options for the conversion specifiers. That's probably a couple weeks to really get a good handle on. Our philosophy has been, we're learning programming through experience. So at least as a start for us, a good starting point would be percent %d for decimal, percent %s for string, we'll be using that early on, percent %f for float, and sometimes when we want to print data that doesn't really correspond to something numeric, we would want to use percent %x for printing out as hexadecimal, and we'll do a little bit of that later on in this particular learning module. And if you need something else, I need to print out a float that uses 3 digits of precision past the decimal point. Well, it's actually percent %.3f. Okay, but for those cases, you look them up when you need them. And that's okay to Google that, to have that page open for the reference, to look at it only when needed, to ask that question. I don't know how to print out with 3 decimal digits. I'll share with you how to do that. I don't know how to pad with zeros. There's an option for almost all of those possibilities here. But percent %d gets you started. Percent %s we'll be using quite a bit. Percent %f as well. So to start with, at least, that is our syntax. We declared a variable integer type called numDogs. We declared a second variable called numCats. And at declaration time, we initialized them to 3 and 4. Again, we could also do that afterwards. And it's not one or the other. We could also initialize numDogs later on in our code. But we initialized it at variable declaration time, and that's perfectly fine. And then now we have that printf that gives us the result of what the number of dogs were and the number of cats were. So you have 3 dogs and 4 cats. That is a very common debugging mechanism. Obviously, for this example, we're not learning a lot about the state of our program, but adding those printfs, printing out the value of variables, is a real good way to understand what's happening inside our program. A sort of companion function that we want to use as connected with our printfs is referred to as scanf. Scanf is a way to read in inputs from the user, and for a lot of our programming practices and our testing apparatus for our programming practice, we're going to want to be reading an input from the user. Why this syntax works exactly as shown here is something I don't necessarily want to cover in depth yet. But for now, I think it's okay to kind of take it as something just to memorize and learn and copy and paste from other examples. With that scanf function, we use a very similar kind of format conversion specifier, in this case percent %d and percent %d again. And instead of passing the names of the variables we'd like to actually update, we're actually passing the addresses of those variables. We're passing them by reference to that function. So the ampersand operator is referring to the address or the pointer of the corresponding variable. Later on, as we start to play around with strings, we'll see that strings are arrays. They're arrays of cars, and we'll see that the name of an array is also a pointer to its first element. So as it turns out, we'll use the ampersand operator for like things like ints and floats and individual cars. When we want to read an entire string using scanf, we'll see we just pass the name of the array. That's annoying. We'll have enough examples that I'm not going to hang you out to dry with learning how to use that properly. But otherwise, the syntax is kind of comparable to what we're already doing for our printf. We're specifying what variables we're hoping the user is going to be entering in with our scanf example. We're potentially specifying other things that aren't corresponding to variables but are also getting typed in by the user. There's some caveats here with how white space gets consumed, but I will always be providing some pointers for how to do that when that comes up in a program. And so this kind of design pattern turns out to be, extremely common, where you would then have, instead of hard coding an initialized version of num dogs and num cats, you would instead have some sort of prompt. And the example we had there is, let me know how many dogs and cats you have. And leave a little space there so someone knows there's a little prompt there. Then you would call that scanf function. I'm going to look for an integer, followed by a space, followed by an integer, and that first integer is going to go to num dogs, that second integer is going to go to num cats. If instead I wanted to have a comma in between them, that would also be fine. In this case, given what was listed on the slide, we're just printing out or reading in integer and integer. Let me know how many dogs and cats you have. We can do 4 dogs and 5 cats. I have a very full household, and it'll print out you have 4 dogs and 5 cats. That is a very common way we're going to be feeding in inputs to our program. Another way you're going to see for the programming practices we're going to want to be feeding in inputs to our program is to use standard random number generation. So scanf is one way we could do so. Another approach is to instead just use random number generation. The function's called rand, and the result of the function that we call rand can be stored as an integer variable. So when we call the function rand twice, we're going to get some random number. It turns out to be potentially a very large number we're generating, and that's quite a few dogs and quite a few cats. One approach we can take is to take the remainder of a value divided by some other value. So I'm going to take, that syntax is wrong. We're going to take rand modulo 10, or the remainder when that random number is divided by 10. It's going to be the same. It's going to print out 3 and 6 here. That's the remainder when we took that very large random number and divided by 10. The remainder when we took that very large value and divided by 6. And then as it turns out, we'll be reading in a random number seed generator, not to get too far ahead of ourselves, to allow us to generate a lot of different inputs. Yes, it's not that hard to read in a number of dogs and a number of cats. It's a lot more work to read in 5,000 numbers. I wouldn't want you to have to type in all those things. We'll do random number generator instead for those circumstances so that you're not having to type in a bunch of stuff to actually test your programs out. There's a lot there. Maybe it sounds simple to you, maybe not. A large percentage of problems in C programming relates to dealing with memory accesses in our code. I made up that number of 73%. But it's a large number of the bugs in our C code is going to have to do with accessing memory. And in fact, specifically for those of you who are more interested in the cybersecurity side of things, software vulnerabilities based on incorrect memory accesses in C code is a billion-dollar issue every single year, despite all the approaches taken to kind of understand memory safety and programming better. So you're going to have bugs when doing this, but I guess everybody has bugs with doing this. So don't feel bad when you're facing bugs working on accessing memory in our code. Again, variable types are abstraction, a way of simplifying that process, but we're still ultimately accessing memory in our code. And if we don't do so carefully, it can lead to all sorts of somewhat challenging bugs to deal with. So as an in-class exercise, in just a moment here, I'd like you to pause the video. I won't have a long delay here. And I want you to think about part of our problem-solving process discussed in the previous learning module was abstraction. Understanding what are the important things in my program, what are their relationships, and trying to assign variables to those quantities. I don't care as much about the variable name, although that is also an important part of the problem solving process, but the variable type here. So as you pause the video here, I'd like you to think about the following 6 types in C: our regular integers, our unsigned integers, our shorter integers, our really short integers or our character types, our char types, our single precision floating point values, and our double precision floating point values. And I'd like you to think about what is some variable that would need to make use of a given type and for what reason. I'd like you to think about that because we're always going to be doing that in our programs. I need to understand the relationships between my data, and I need to understand before I type a single thing in my code, what variable types make sense for my program. C makes you think about this as a first order of business in writing your program. You can get pretty far with ints, but we'll see quickly here that if you're not careful, ints actually aren't going to be sufficient for a lot of even simple programs we would want to write. So pause the video here and think about and come up with 6 different variables, some that can use ints, some that can use unsigned ints. And if you have any questions, this would be a good time to first join our Discord and say, hey, I got to lecture 12 or slide 12 in the second learning module, and I have no idea what you're talking about. It's a good time to pause as opposed to trying to continue on because we're going to be using these types, and it's going to start to pick up here in just a minute. Okay, I'll be curious to see what you came up with. Let's talk about memory a bit more here. I don't want to get into all the details of two's complement representation and binary representation, but as I mentioned, our memory is in reality is just filled with binary values. Individually, we refer to those binary values as bits. Our zeros and ones, they correspond to actually voltage values stored in some physical thing built out of semiconductor technology. It's a 0 or 1, that's why it's binary. It's one of two things. We generally group those bits together to represent more complex data. So you don't hear the term nibble all that much, that's 4 bits. A byte is just our 8 bits of data. Half word is a common term for a 16 bits of data, or a word, 32 bits. Sometimes double word is 32, other times it's 64. 8 bits being a byte is a pretty universal thing. There's an inherent limitation to how we represent data. I don't think we'll fully appreciate this as of yet, but with I bits, we can only uniquely represent 2 to the I different values. So if I have 8 bits to store a value, like we have for our 8-bit char type, I can only uniquely represent 2 to the 8, which happens to be 256 different values. So when we see that a regular char can represent negative 128 to 127, that's why, or that's one reason why we can only uniquely distinguish 256 different values. So while technically an integer is any non-fractional number in that negative infinity to sort of infinity range, we generally in our programs only have a fixed number of bits to store our variables and to represent our integers in C. Generally, if we're using a regular int, it'll generally be a 32-bit data type. We can represent 2 to the 32 different integer values with that int data type. But there's an incongruity there. Our integer, mathematically, we may want to represent something much bigger than what we can represent in 2 to the 32 values. And that's why we have to think about our types. How many bits are we storing in this particular type, or how many bytes? We can look at that as well. What is the maximum value we can actually represent? And is that going to be enough for us? We have to answer that question before we can really get going with our programs. A lot of the programs don't deal with that, but I specifically come up with a few examples that do specifically deal with that. And that also is the reason why we have an example kind of similar to this in the second programming practice, which is using the built-in size of operator in C to actually return for your particular system how many bytes the program actually requires. Let me open up that example here. So here is our size of example program here, and it's exactly what was listed there. And the result is, for this data type, a char, it's 1 byte. For a short, it's 2 bytes. Exactly what I did have in that particular table here. Another thing I introduced in this example that wasn't in the slide was this uint8_t type. It's a bit more wordy, Those types are defined in this standard int header library here, and those can be useful when you want to be really explicit in your code about how many bits you're using for a type. This is exactly as it could sound. It's an unsigned integer that uses 8 bits to store that particular value. If instead I want to store 16 bits, I would instead use a uint 16t, and you get a result of 2 back out for this example. It's not arbitrary. You can't do uint 7t. So it's the types that we already have. It's not a new type. It's just a different way of naming the existing types. So you can have an int 64t, and that would be a signed 64-bit integer. That can be useful when you want to be really explicit in your code about the size of your types. We don't use them by and large this semester. We stick with the built-in C defined types. Looking back at our memory and our addresses, we can actually mature our view of memory a little bit here. So instead of just being this arbitrary collection of bits at arbitrary addresses, memory is instead going to be segmented into bytes here. At least in C, we're pretty limited by that. We're not going to generally have data types that use 13 bits or 26 bits. It's going to be some multiple of 8. So we can think of this memory as being this array of bytes that we're individually accessing via these variable types. And the programmer sees the variables, but we can actually see the addresses whenever we potentially would need them. And that's that ampersand operator again here. Um, where here now we're specifying just a few different variables that we have. We're specifying an integer, a short, and 2 characters. And we can use that ampersand operator to print out the actual address of that location of variable A in memory. The result you get when you run this may in fact be different than the result that I get when I run this. It depends on other things, what else is in the memory and system, what result we get back out for the address of that. So we usually don't need to know the actual location, but it does exist and we can print it out. The correct way to technically print out a pointer is not to use %d and print it out like a decimal value, but instead to use %p and print it out like a pointer value. And we can see it's actually a 64-bit pointer because the system this is running on has got 64-bit address space. We can print the other variables as well. Generally, they should be near each other in memory if they're declared near each other in our program. So we'll just do b here. It may actually depend on the system not be after the location memory. It may in fact be before the location memory because it sometimes gets compiled in reverse order there. And we can actually see that that's the case. It's printing out in hexadecimal here, and that's the actual address of A and the actual address of B in our program here. There isn't more I want you to do with this example just other than just to see these addresses correspond to something actual and real in your underlying system the code is running on. We need to use those addresses for various functions like the scanf function. We normally don't need to know that it's 0x7ffccebab4bc. Usually, we don't need to know that that's the actual value that we have there. We got to talk about expressions as well. Let's keep going here. Expression refers to a combination of one or more operands or operators. We'll start with the arithmetic expressions in C. Those are the ones used to compute numeric results, and they make use of the well-known arithmetic operators. So generally, the basic operators are supported. So your addition using the plus symbol, subtraction using the minus, multiplication using that little star symbol, division is the /. We'll use the remainder operator quite a bit for some of our programming practices. That gives the remainder after having done integer division. But as I mentioned, C being a strongly typed language, we do have to be a little careful with how we use those operators. And I'd like to give an example here. I mentioned the several steps with our mailbox analogy. We have to read the value. We have to read multiple values potentially. We have to apply the arithmetic operator, and then we have to store the result back out. We can also use this so-called typecast feature available in the language to at least temporarily treat a variable as one type as instead a variable of another type. This example I'd like to just bring up and show you what actually happens here. Here's our float math example. We've declared an integer a float type b and c. And our first line, what we do here is we say b is equal to a divided by 2. Mathematically, that makes sense. Mathematically, we're saying b equals a divided by 2. A is 5, b should be 2.5. Later on, next line, we say c is equal to a divided by 2, but first we typecast a as a float. You can actually see the results when we print them out are different though, right? When we print out b, the result, even though b is itself a float, is not 2.5, it's actually 2.0. Only when we did the typecast to float did we get the correct result for c is equal to a divided by 2. And that has to do with the properties of integer division. When we do this expression here, we have an integer a, we have an integer 2, and we're doing an integer division between them. Integer division doesn't keep track of any remainder or any subdecimal precision here. So we take 5, and we divide it by 2, and we actually get a value of 2. And then when we assign it to a float, it actually does get assigned to a float, but it's not 2.5 at that point, it's 2.0. Instead, now syntactically, we can do a typecast of a. So at least temporarily, we're saying, temporarily, for the purposes of this expression, treat a like a floating point value. Then divide it by 2. And then that would actually now treat it not as 5, but then as 5.0 temporarily. Now when we divide that by 2, that's well defined to give us our result of 2.5 here. That's one approach to making sure our integer and our floating point math works correctly. Another approach is referred to as promotion of a type, that if any part of the arithmetic expression uses the higher precision type, they all get promoted to that type. So just by taking a and dividing by 2.0, and let's actually do that on this first example here. When we divide it by 2.0 versus 2, that then promotes the a to 5.0 first. We get 5.0 divided by 2.0 versus 5 divided by 2, and we get the correct result there when we do that. That's going to come up as you're writing programs. I'm not going to deny that. When we are dealing with integer values, but we actually want to know the average of 5 integer values, well, how do you calculate the average of 5 values? You add up all 5, and then you divide by 5. To get the correct result when you average 5 values, you can't divide by 5, or if you do, you have to typecast as a float first, or you can divide by 5.0, and that'll also give you the correct result. Sometimes you want to do just 5.0 or 5 divided by 2 to get a result of 2, but if you don't actually want to do that, you have to make sure you do that typecasting properly. And finally, let's talk about operator precedence. By operator precedence, I'm referring to which operators happen first, because as with all languages, you can combine individual operators into more complex expressions. So in this example, the result is equal to the total plus the count divided by max minus the offset. Just like when you learn basic arithmetic in elementary school, there's this PEMDAS order of operations, or GEMDAS, depending on how you learned it, or if you learned some other system. That defines our order of operations, and it's effectively the same exact thing for C programming as well. We do multiplication, division, and remainder, which are done first from left to right. Arithmetic operators are generally done from left to right, but you can use parentheses to force the evaluation order to do all the things within parentheses first. So it's effectively PEMDAS. We don't have exponentiation like this, so it's really just the multiplication and division and remainder modulo operator having precedence over addition and subtraction. If you need to reverse that order of operations, you need to use parentheses to group the arithmetic operations first. Here's a quick example that shows those order of operations. We have first expression, although we're not assigning to a variable, you can imagine we could assign it to a variable, a plus b plus c plus d plus e. Those are all addition. They have all the same precedence order. We're going to do addition from left to right. So we'll do the a plus b first, then the b plus c, then the c plus d, then the d plus e, and it's going to accumulate those values and do the operations from left to right. A plus b, that result plus c, that result plus d, then that result plus e. The next example to the right here, a plus b times c minus d divided by e. Multiplication and division have higher precedence than addition and subtraction, so that b times c is going to happen first. We'll go from left to right, then the d divided by e, then the addition, then the subtraction. Same goes for the next example, which also has the modulo operator here, but now we have parentheses. We've put parentheses around b plus c, and we're going to do our parentheses first. So b plus c is going to happen first, then we're going to take a divided by that result, Mathematically, the assumption is that's what we want to have happen. We need to have the parentheses to enforce that order of operations. So A divided by B plus C, then we do the modulo operation because we do that as higher precedence than the subtraction. Then finally that subtraction happens. And we can have these nested parentheses as well. D minus E is the most nested parentheses. That would happen first. Then C plus that result. Then B times result. Then A divided by that result. I think it's okay to say that when in doubt, add more parentheses. When you're not sure if you're getting the right order of operations and you're doing things exactly correctly, just make sure that you have the set of parentheses around it. And of course, use printf as your debugging tool. That's critical as well, right? Use printf. Did you get the right math? Provided a couple values for A, B, C, D, and E. Did you get the result that makes sense? If not, take a look back, make sure you're following the order of precedence properly, and then add parentheses as needed. And my final point I want to make in this video, which I know is going a little bit long at this point, is characters and the related string types are also critical to programming in C. I mentioned the char type is this kind of short integer type that uses 8 bits to store that values, but it can be more than just a small integer. So it is both a small integer and it can also encode via this ASCII representation actual text characters. In C, if we want to specify a character literal, an actual character like an a B, or a C, we would use single quotes. Both of these initializations on this slide are valid for that reason, because a char can be either, can be both. It could be an actual character in our ASCII table, as I'll show on the next slide here, or it can be a small integer value in that range -128 to 127. And it's not either, it can be both. And you can sometimes treat it as a character to be printed, and you can then treat it as an integer within the same line of code or within different lines of code within the same program. We sometimes want to do that. If I want to know, which letter of the alphabet is, we can take the value of our character, subtract A from it, and get knowledge of which offset from A is it in our ASCII table. We can then combine our character literals into string literals, and that uses the double quotes then in C. With printf, we've already been doing that for hard-coded strings. We'll have actual string data types as well. That's a whole separate learning module in this course, not because it's that different from what you would have already learned to that point, but because we really have to be adept at using the string handling functions in C to be effective C programmers. This figure is one that you may have open in a tab while you're working on various programs. This is one version of the ASCII table. It is a standard that represents for our different char values, in this case from 0 to 127, what character can that potentially correspond to? Some of those are printable on a string, others are not printable on a string. Some we've actually seen already, like our new line, that's actually decimal value 10. If I were to print out 10 as a char in my code, it would actually print out a new line. But we can actually see a lot of the characters we would want to use are here. So if I want to print out the number 0, I can take a char and actually store 48 to it, and it'll print out as the number 0. That may seem a little counterintuitive. You'll want to have a printout of this table handy as you're working with C programs, that if you want to print out the character 0 and have a variable that stores the character 0, you don't actually store the number 0. You store 48, or just the string, the character literal of 0 in single quotes there. Likewise, for our A through Z, the capitals come first. The capitals start at 65, the lowercase start at 97, and there's some stuff in between Z, capital Z, and lowercase a there. ASCII is a standard. It's been around for decades now. It's also pretty limiting because the real world uses Unicode and has a lot more than just basic A through Z, 0 through 9 kind of characters we want to print out. We'll use some Unicode sparingly. Most of the functions that work with ASCII also work appropriately with Unicode. We'll shy away from some of the trickier aspects of Unicode and stick with ASCII by and large for our printing, because there's a lot of fun things we can do with just basic ASCII text. That was a lot to cover. As I said, kind of a fire hose of information. This would be a good chance if you have any conceptual questions, please feel free to post them in our Discord, and I'd be happy to answer them. Otherwise, stay tuned for the next part of this topic where we'll look at some in-practice exercises using our number representation and what we can do with our variable types. Otherwise, good luck on your first programming practice, and I hope to see you soon.